Hello, it's your host Sam Hansen, and I'm excited to welcome you back to Carry the Two, the podcast for the Institute for Mathematical and Statistical Innovation, about how math and stats impacts the world around us. While we're in between our more in-depth seasons, we like to bring you something a little different in mini-season format. And for this mini-season, we're going to highlight some of the amazing researchers who have presented at IMSI over the past year. Our sixth and final guest is...
My name is Lars Peter Hansen.
Lars is the 2013 recipient of the Nobel Memorial Prize in Economics and a professor at the University of Chicago.
I have appointments at the Economics Department, the Booth School of Business, as well as the Statistics Department.
Lars joined us at IMSI for a workshop on economic impacts of climate change, where he presented a talk titled, How Should Climate Change Uncertainty Impact Social Valuation and Policy? So, without further ado, let's get into my conversation with Lars Peter Hansen. When you're talking about designing policy, what are some of the trade-offs around policy design that have to do or are related to uncertainty?
I think that there being two important trade-offs that uncertainty puts on the table. The first one is the following. When we build mathematical models, we can use them in multiple ways. One way we might use them is the fact to allow us to make best guesses. What's going to happen in the future? As I change policy, what's my best guess what's going to happen? The other way to use it is to say, well, what could be more extreme outcomes, an adverse outcome, for instance? What's the possibility in terms of things that might happen and things I might want to be worried about? Both those uses of models are very important and can be very valuable. There's an interesting trade-off between how much weight you put on best guesses versus how much weight you put on more extreme outcomes, especially the adverse ones. If you spend all your time on best guesses, there may be a non-trivial possibility of something bad happening that you've ignored. If you only care about bad outcomes, then you may just give up and not get up in the morning because things could be so terrible. Really, in decision making under uncertainty, there's a place in between that you want to be, and so that's one of the trade-offs. The other one I think is very important is, do we want to act now, or do you want to wait until we get more information in the future? There's always a temptation to say, well, since we're going to figure more stuff out in the future, let's just wait. But it may be very, very costly to wait until the future. It may be more prudent to act now under the possibility of particular outcomes happening instead of waiting until you're completely confident that such outcomes will indeed happen.
And so if we're talking about policy around climate change and global temperatures and things like that, what are some of the uncertainties with the economic impacts of that you would study?
So the ones that we study, and these are not all of them, are four. One is the usual one that economists study about. If I make certain investments today, they're going to have longer term uncertain payoffs, successes. And so economists have studied this one in terms of investment problems for many decades now. It's kind of fundamental to economic dynamics. So that one's there. Ones that become a little bit more unique to climate change would be, imagine that we emit carbon in the atmosphere today. That's going to impact, say, temperature, or more generally the climate system in the future. What are those kind of longer term impacts on climate change of carbon emissions today? The third one has to do with, if we have climate change in the future, what impact is that going to really have on economic opportunities? Of course, economies have historically adapted to different type of environments and the like. There'll be some adaptation that might take place. There may be some rearrangement of the productive capacity of the economies and the like. At the end of the day, what are the economic consequences of this, and how will economies respond to them? This comes under the heading of what environmental economists would call damages. The final one has to do with technological progress designed towards helping us with climate change. So as we engage in research and development today for the discovery of new technologies that might remove the need of fossil fuels, there's different possibilities on the table. We're not sure about their payoffs, when they will pay off, and exactly how successful they will be. But on the other hand, it makes sense for society making some investments in these type of technology changes. So what will technological progress be in the future that's relevant to addressing climate change?
How did y'all go about starting to study? Like, what was your approach for studying these uncertainties?
Kind of in a nutshell, what we do is we start off and come up with baseline type specifications. These specifications include things like random shocks, and so there'll be probabilistic specifications. We have dynamic stochastic models which we use to analyze things. So we start off with some baseline type specification, and many analyses start there and end there. Okay. For us, then we need to. So here we need to have inputs from the different components which I described, and then they're going to interact in the context of the model itself as we do as we start solving and analyzing ramifications for different economic policies. So for us, that's a starting point and not the ending point. We also then want to start asking, well, these baseline probabilistic specifications are, in some sense, guesses. We're not completely sure they're right. There's often simplifications made to kind of simplify the numerical analyses as well. What are the consequences of us not being quite right there? What are the consequences of we're not 100% sure that that's the right specification? How do we then look at the ramifications of that? And if things could be off, where are the sources of it being off that really matter for the decision problem, for the policy design? Not all mistakes are going to be, or not all kind of changes here are going to be equally impactful in terms of the design of a prudent economic policy. So part of what we're about is to kind of at the same time be building numerical techniques that help us understand where the uncertainties really matter. Once we identify where they really matter, then that can open the door to further scientific investigation, seeking out better information along some dimensions, or investing, say, in knowledge accumulation going forward.
And if I understood your talk properly, I believe that you started to then use an area called decision theory to dig into some of this. So how can decision theory or a decision problem help you determine which of these uncertainties or where these uncertainties are most consequential?
The uncertainties potentially for models like this can be very high dimensional. I've already outlined 4 different channels of the uncertainties could affect things. Each one of those could be, have kind of a certain type of richness attached to it. And so opening the door to different places in which things, there might be ambiguities in the specification, there might be potential concerns about misspecification. The decision problem, when you put it on the table, then allows us to say, well, among all these high dimensional uncertainties, which ones really matter? So we use the decision problem to figure out, to sort through these higher dimensional components of uncertainty and to figure out the ones that are most impactful for the problem at hand. Without a concrete decision problem, then we'd just be left with high dimensional uncertainty, and that would be it. But for us, we need to take uncertainty quantification beyond just the characterization of the uncertainties, but to ask the so what's of the uncertainties. And that's where this notion of a decision problem comes into play.
So what was the decision problem that you used when looking at the climate change uncertainties?
We took a what I would call a highly stylized initial approach. That this is not the end game; this is the beginning game in many respects. We consider this hypothetical, which we call social planner. This person to say, well, I'm going to look at the global system, and I'm going to try to figure out what would be the most prudent thing to be doing. Now, of course, actual policy making is far more complex than that. There's multiple players on the table. The players may have different incentives, different objectives, and the like. But for a starting point, we take this kind of what we call this fictitious social planner approach. And then we analyze the various different sources from the perspective of that. So we're going for what would be the ultimate kind of well-designed climate policy. And then we can start adding in more complexities to the policymaking process as well, which is indeed very important, but we're just taking this initial step.
If you're getting a lot out of the important research shared on this show, there's another University of Chicago Podcast Network show you should check out. It's called Not Another Politics Podcast. Not Another Politics Podcast provides a fresh perspective on the biggest political stories, not through opinions and anecdotes, but through rigorous scholarship, massive data sets, and a deep knowledge of theory. If you want to understand the political science behind the political headlines, then listen to Not Another Politics Podcast, part of the University of Chicago Podcast Network. I also want to let you know that New York Times bestselling author Stephen Strogatz is giving a public lecture on mathematics for biological discovery and biology as inspiration for mathematics on Wednesday, May 7th in downtown Chicago, hosted by NSF's Simons National Institute for Theory and Mathematics and Biology. Strogatz's research has helped uncover the mysteries of the human sleep-wake cycle, the collective behavior of firefly swarms, and more. Get your free tickets at nitmb.org. And so for this analysis that you did, what did it tell y'all about these different uncertainties with regard to policy? Like which of the uncertainties came out as, I don't know, the winner or the loser?
Yeah, right. So it was a little bit of a surprise as to how this played out. There's been lots of considerations of so-called this damage uncertainty. We're pushing economies into places that they haven't experienced historically, so we can't just look at historical evidence and say, well, here's what's going to happen. These so-called subjective components to model building, in this case, and damages are a key place where that's the case. So there's been lots of people conjecturing that damage uncertainty is a big deal, and we would agree with that. We were looking at a particular type of technological change. That is kind of the big project change. The kind of climate analog to building atomic weapons during the Manhattan Project, or the climate change counterpart to putting astronauts on the moon or the like, ones that don't require some type of very big investment. One could think about this. The type of investment could be a nuclear fusion technology, which is highly uncertain, but has a promise that if it does get developed in an economically viable way, could really have major impact in terms of addressing climate change. So we were looking at these big project type research and developments there, and it turns out that kind of dominated our uncertainty. That's the one that really mattered the most in terms of our calculations. So that's the one thing. So we put in these different 4 channels, and that's the channel that kind of mattered the most, with the damages coming in next as kind of the second most. And then the way we do this, roughly speaking, is we imagine activating all the channels simultaneously, and then activating one at a time, and see which form of uncertainty gets us closest to the ones where we're activating all simultaneously. And this is the case. This research and development type uncertainty became the important one. So that showed up. Now, there's another aspect of this calculation that initially surprised us, and we now have a much better understanding for it as to why. Usually, when people think about investment problems under uncertainty with multiple choice of investment, one thinks about, well, you make society more averse. Okay, so part of this decision problem is you have to decide how averse society should be to these uncertainties. That's a statement of societal preferences. So we can hypothetically ask, if we make society a little bit more averse, what's going to happen to these social investments in things like research and development? And so for standard investment problems that people analyze in finance, it'll often be the case that if you increase this aversion to uncertainty, you want to do less of it because you're less sure of what the prospects for the technology, and you'll kind of shift towards ones in which you're more confident in. In this case, we were finding the opposite. We were finding that even though when he made our decision maker more averse to this uncertainty, less confident in these baseline specifications, when we eliminated that confidence, the policy was to be more proactive, not more passive. And so that became a very intriguing part of our finding, and that we've been spending time trying to contrast or trying to explain exactly why that's the case.
You said that you do understand that a little bit more now. So can you tell us a little bit about what you have found since about this aversion?
Sure. So there's two offsetting forces. One is the one that I just described that would show up in a lot of kind of standard investment problems under uncertainty. That is, if you make the decision maker more averse, it might well do less of it, and shift towards investments that would be that there's more confidence in. But here, this problem, and what makes it different than a lot of more standard problems coming out of finance, is the payoff itself. So we have to think about, how about a success? How about an R&D success? And R&D success itself, we have to compute what that ramification is as part of our model solution. So we're actually figuring out, how important is it to society to have the success, or what's the value to it? And the relative value to that success, if you make that person more averse, actually is higher relative to not having the success. So what's different from a standard investment problem is that when we're changing this aversion, we're also changing the consequences of a success here. And so if you make this discovery, you've eliminated a big chunk of uncertainty going forward, and that's a big winner. And the more averse you are to uncertainty, the bigger that win is. So there's this first channel, which, I'm not quite sure when this is going to pay off, and I'm not very confident in that. That makes you want to do less. But then the consequences of a success make you want to do more. And so we show that quantitatively the second one dominates.
That's fascinating. And so once you've done all of these analyses, once you've completed these studies, how would you then go talking to people who are the policy makers, the people who are actually implementing these things? How would you approach them and talk about how you understand these uncertainties in a way to help them make the policy more effective?
Yeah, that's a good question. So my own direct communication with policymakers has been more to actually central bankers than others, although there's been a little bit of other connections elsewhere. My view on that is the following. To go to the actual final decision maker, they're spending all their time trying to sell things to public and the like, and the people you can have the best chance of influencing are the policy advisors. And they're the people who would have the patience and maybe the background to understand how these arguments really work, and then let that person translate or figure out the way to sell it to the out front person trying to market the policy to society. So I think our best hope is to be able to influence the advisors to the different policymakers. And for various projects, I've just described one of the projects which we've been doing. We've been doing other work on, the Amazon rainforest, and my colleagues have been spending time talking to a variety of policymakers about. You can have successes in talking to the advisors, especially since some of them have some very sharp and very sensible advisors.
And so I have one last question for you, and that is, how was it to be a part of the workshop at IMSI? Like, was it a good experience? Were you able to make connections? Did anything positive come out of it?
So the thing that was advantageous there was the following. I find workshops of this type to be valuable when we bring people in from applied math and from people that kind of use applied math to actually solve substantive problems, and to have those conversations go back and forth. And so the presentations themselves were of some value, but maybe just as much value are the more informal conversations that evolve afterwards. They evolve over coffee. They evolve over subsequent meetings. They open up dialogues that might not otherwise be there. They nurture those type of communications. And I think to address problems like, say, climate change, it becomes very important to be drawing on expertise across the board, including kind of mathematical and technical expertise. We're coming out of INSEE, we're now like collaborating with people that are better, even more expertise than we have in terms of computations. We're having some conceptual discussions with other applied mathematicians and the like, and so it helps us to understand what the frontier of possibilities are there, because it's very hard for me to keep track of all this on my own. Having these conversations, though, and opening the door to collaborations could be very, very valuable. So that's what I see as the big gain. That there's this opportunity for conversations cross-disciplinary in nature.
Lars, thank you so much for giving me your time today.
Sure. I hope this is what you're looking for.
And that is it for this mini season of Carry the Two. We will be back soon with our next in-depth season, where we will be digging into the mathematics and statistics of emerging technologies. As always, don't forget to check out our show notes in the podcast description for more about Lars's research and to watch his talk. And if you like this podcast, please make sure to follow, subscribe, or like the show in your podcast app of choice. It is the best way to make sure you hear all of the episodes of Carry the Two. For more on the math research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. That's IMSI.institute. We're also on Blue Sky at imsi.institute, Twitter at imsi_institute, as well as Instagram at imsi.institute. Do you have any mathematical or statistical questions? Maybe you have an idea for a story on how mathematics and statistics connects with the world around us. Send us an email with your idea. You can send these ideas, your feedback, and more to sam@imsi.institute. That's sam@imsi.institute. We would also like to thank Blue Dot Sessions for our music. Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We are supported by the National Science Foundation and the University of Chicago.